Het is een gigantisch weer een wereld op zich, dus er is ook heel veel om te leren weer. Maar goed, we zijn over 1 minuut al online, dus anders zal je zo al aankondigen. Ik ga mijn video uitzetten. Succes!
Hoi.
Hello, everybody. Welcome again at the International Conference Use of R in Official Statistics, third day. It is my pleasure to invite our colleague from Statistics Netherlands, Jan van der Laan, to learn us about his package reclin. And the topic is probabilistic record linkage using reclin. This is a 2 hours time slot tutorial. You are invited to follow him via YouTube link. You can ask there your questions, and I am going to transfer the questions and the replies between WebEx and YouTube. Good luck.
Yep, thank you. Yeah, I will start by sharing my presentation. So this tutorial will be on reclin, which is a package for probabilistic record linkage and deduplication. I will, during the tutorial, I will be doing quite a lot of demoing of code. And yeah, should you want to type with me, then you can download the material at the GitHub site at the bottom of the slide, and I've also pasted the link in the YouTube chat. And there will also be some exercise, so there will be a couple of moments where I will stop talking for something like 10 minutes, and you will be expected to try to use reclin, and you can then ask questions in the chat, and I will reply to them. So let's start. Maybe first a little bit about me. I'm a methodologist, data scientist working at Statistics Netherlands. I've written a couple of R packages which are on cron. There are also a couple of that are not on cron but are used internally. Well, this, for reclin, my most recent package is a simple R Markdown. LOF is a package that can be used to read and treat large ASCII files. And then there are also two packages, ldap and lvec, which are also used by reclin, that can be used to store large data sets partly on disk. At CBS, I give multiple courses, usually with R. So I'm having a couple of courses on different multivariate analysis methods, and also give a course on using R in statistical processes. Now, maybe a little bit more about the other non-R stuff. I'm doing a lot of work on social network analysis, and also at the moment running a large project where we try to measure the socioeconomic status. And also using the network, we're also trying to measure segregation. So these are projects I'm currently working on, and most of them are also largely in R. So this is the outline of the tutorial. First, I will give an overview of record linkage. Then I will discuss the traditional record linkage, so the Felix-Hunter method of doing record linkage and using the EM algorithm to estimate the parameters of that model. I will also talk a little bit about string similarity and also custom similarity functions. So yeah, I'll come to that later. And finally, I hope there's still some time left to discuss how you can use machine learning with reclin to do record linkage. So the basic idea is that each item consists of me talking for 10-15 minutes, and then there will be something like 10 minutes for you to work on the exercises. And yeah, the largest part of me talking will be basically in R, doing a demo and explaining stuff. I will first, I guess that most of you have seen my talk on reclin also during Wednesday. I will revisit some of those slides to give a bit of background to reclin. So what are we trying to do during record linkage? So what we are trying to do is to detect which records belong basically to the same person. So in this example, we have two persons, John and Jane, and we are trying to detect which records. So each person generates basically records. It can be within the same data set, or it can be between different data sets. Or this can be for population register, and this can be for example text data. And what we want to do is to determine which records basically belong to the same person. So when we are looking at one data set, for example, so let's say that this is one data set. So each person generates multiple records within the same data set. In that case, we're talking about deduplication. So we have multiple records belonging to the same person within the same data set. And we're trying to find out which of those records belong to the same person. And we're talking about record linkage, you talk about two data sets. So you have one record in one data set and the other record from the bottom one in the other data set. But the techniques are largely the same. Now, well, the first step in record linkage is to compare records to each other. So we are going to compare records from one data set to records in the other data set, and we're going to generate comparison vectors. So in this case, we compare the record of John to the record of Jane in the second data set, and then we have this is an example of a similarity vector. So we have a partial agreement on first name, complete agreement on last family name, and no agreement on age and gender. So we generate these comparison vectors, and that is something that you want to do for each combination of records from both data sets. So in this case, you have two records in one data set, two records in the other data sets. So there are 4 different possible combinations, 4 different pairs, and each of these pairs we will compare to each other, resulting in 4 comparison vectors. Now we have these comparison vectors, and the next step is basically to calculate a kind of likelihood score that these 2 records of a pair belong to the same person, basically. So we score those comparison vectors, and there are a number of ways to do that. One is, this example is a really simple similarity measure. We basically sum the comparison vector. Another way of doing it is, for example, using the traditional probabilistic record linkage, basically the validity center model, to calculate the likelihood ratio. But you can also use machine learning for this. So you can basically treat this as a feature vector, and you have to, and then the output is generally a probability that those 2 records in the pair belong to the same person. So we score those records, and then the final step is to select them, and then when we've selected the pairs, we have basically linked the data set. So that's the final step, to create from these selected pairs the actually linked data set. So this is an overview of what I just mentioned. So we just first generate pairs, then we compare the pairs to each other. We then have to translate those comparison vectors into a likelihood score, or a probability, or at least a score that corresponds to a likelihood of belonging to the same object. Then we select the pairs, and then finally we generate a linked data set. So these are basically the steps. And one of the goals of reclin, I try to build reclin in such a way that is kind of basically a toolkit. So we have functions for each of these steps. We have functions to help you on that. And you can basically mix and match those functions to create your own linkage process. And the goal is also to make it really relatively easy to for example, let's say you want to do some complex comparison that's not present in reclin. It should be quite easy to write your own comparison function, for example. So I think it's a tutorial, so I will switch to R, and I will start showing how reclin helps you in those steps. So I'll stop the share, and I will switch to RStudio. This one. I will save my code. So I might add it to the repository later, or maybe after a little bit of cleaning up. I have downloaded I've downloaded the dataset actually from GitHub. So what we have is, in this case, we have the exercise that you will be working on later. And then there are a couple of datasets. And in my demo, I'll be working with the first two datasets. So I will start with reading those two datasets into memory. So reclin is on cron. So you can install it just using install package. Of course, I've already have it on my computer. And then, I will first read the two datasets. So we have the first dataset. I'm in the wrong directory, sorry. I also followed the previous tutorial, so I was in the wrong place. So now should be in the right place. Okay. So I will read the first dataset. I'm still used to doing strings as factors is false, but it's nowadays default. And the reason for that, we have some text fields, which are actually text fields, not categorical variables. So we want to read those as factors, but as text, and not. We'll first show the datasets, I think. We have two datasets. They contain records about persons. So for each person, we have a first name, a last name, a sex, date of birth, month of birth, year of birth, and a postcode. And what we want to do is, we want to link those two datasets to each other. So we want to determine which records on the first dataset are the same as the records in the second dataset, and vice versa. And what we will see later is that there are errors in this dataset. So that's of course the reason why I use probabilistic record linkage. Is the case where you don't have perfect data. So there are errors in this dataset. There are missing values in some of the variables. There are typing errors, especially in the first names. There are quite a lot of typing errors. For example, here you already see a typing error. So in this case, it's probably Charlotte, but the H is substituted by an M. And the goal is, of course, to link those records to each other, to link the datasets to each other. So in the other dataset, the name might, if Charlotte is present, there's a really big probability that she's called Charlotte with an H in the other dataset. So we can't directly link those two datasets to each other. We have to take into account that there are errors in those variables, which is, of course, the goal of probabilistic record linkage. Well, as I mentioned, the first step of record linkage is to, at least in reclin, is to generate the pairs. There's a function called pair underscore blocking to generate pairs of records. I will give my first data set and the second one. I will just do it like this. And we will look at the output. Oh, there are a couple of things that we can see. I will start with what we see here. So what this basically says is that the first pair is basically comparing record 1 from the first data set. It's called X internally by reclin to the first record in the second data set. And here we compare the second record from X to the first record of Y, etc. And if we look at the size of this, we see that we have something like 10 million pairs in this data set. Another thing that you might notice is that it says here ldap. I already mentioned the package ldap. There's a package by me which can be used to store data on disk. And the reason for that, the reason for using ldap within reclin is that As you can see, we already here have 10 million pairs. So these data sets can quickly become very large. And generally, if you, I'll come to that later, if you don't do blocking, it's basically the product of the size of the two data sets. If you take a data set and multiply it by the size of the second data set, you have this, this is basically the number of pairs that are generated. So in this case, the data sets are not that big. I mean, the data set is something like 3,000 records, and the other one is of a similar size. So with only two data sets of 3,000 records, you already have 10 million pairs, and you can imagine how big it becomes if you have records with millions or hundred thousands of records, and it's quickly it's becoming really, really big, and then it doesn't fit into memory anymore. And that's where LDAP comes into play, because it can store data partly on disk. The disadvantage of LDAP is although it behaves largely like a data frame, it's not an actual data frame. So not all operations that would work on a data frame work on an LDAP object. In this case, the data are not that large, so I will be working in memory. And you can say that by saying large is false. We generate the pairs again, if we print those two. At the pairs to screen. Now the pairs object is in the, if you look at the data set, it's basically a data frame. So you can basically use the pairs as a data frame. And this is also, I think, one of the core things of reclin is that basically the output in generally, especially if you use large false, is a data frame. So you can really easily do your own manipulations on that. It's no problem if you derive your own columns in this data frame or do other manipulations, filtering or selection or deriving your own variables. You can all do that, and reclin will still work. So now we have compared the two data sets to each other, and as I mentioned, the size is basically quadratically. So you multiply the size of the data sets, and that's the number of pairs that are generated. So that can quickly become very large. So what is usually done in record links is that you try to contain the number of pairs. And one of the ways of doing it is by using what's called blocking. And when you do blocking, you only compare records that agree on some blocking variable. So you can think on, for example, of a region. So you only compare pairs within that are living within the same region. Or you can compare pairs that have the same year of birth. Of course, disadvantage is that you might miss pairs. So if there are errors, for example, in year of birth, and you compare, let's just start first by seeing how that works in reclin. Large is false, and we want to block on date of birth in this case. This. So what we now see is that, well, previously we had something like 10 million pairs. Now we are only left with 128,000 pairs. And the reason for that is we only select records that agree on year of birth. So what that basically means is that we assume that year of birth has a really high quality. That we can assume that there are no or very few errors in date of birth, birth year. And we only compare records if they agree on year of birth. So we're only comparing records to each other that have the same year of birth. So the advantage is that the number of pairs is drastically reduced. So we went from 10 million to 128,000. So that's a really big reduction in the number of pairs, and also the computational complexity later on. The disadvantage is, of course, that we might now miss records that belong to each other that have, for example, an error in year of birth. So one way of resolving this is to use different blocking variables and to have to link a data set, for example, twice, once on year of birth and once on region, and then combine those results with each other. And then you are only missing pairs that have errors in both region and both year of birth. So with so now we have the pairs that we will be working with. But we only started to compare records that agree on year of birth. And now, yeah, we can work, we continue the work on this. Maybe to get back a little bit on the sizes that you can get with the record linkage, the code that was the code where reclin was based on, we had a really big project that was basically a sort of after project of the census, 2011 census, where we wanted to count the basically the undercount of our official register. So the Dutch census was based on the population register, but of course not everybody in the Netherlands is registered officially. So by combining different data sources, we want to get an estimate of how many people we are missing in the in our official government registers. So one of the things that we did was we linked, for example, the tax data to our official register. So our official, we have something like 70 million people living in the Netherlands, and of course, for most people living in the Netherlands, for most people yeah, paying taxes, they are registered in the Netherlands, and the remaining part, something like 200,000 persons that we suspect are living in the Netherlands, but were not registered at the official registers. We wanted to link those two datasets to each other. So basically, the linkage problem was this size. So what you end up with is, yeah, well, a really large number of pairs. And I did a quick calculation of how much memory you would need to store this data set, and then you're talking about, I think, something like 100 terabytes of data to be able to compare those pairs to each other. And that's only memory. I mean, computation time would also be immense. So in these kind of cases, you have to do some blocking to reduce the complexity of the problem. Yeah. Let's see. So now we have the pairs, and the next step is, of course, to compare, to generate a comparison effect. So we want to compare both records to each other. So we want to compare records 342 from the second data set to record 1 of the first data set. And you can do that using the compare pairs function. We give it the pairs, and we want to say on which variables we want to compare. Did we have? Yeah. In this case, you want to compare on first name, date of birth, day, month, we're not comparing on year because we already know that those agree, because that's how we generated the pairs. Now look at the pairs. The pairs basically, yeah, what this function does is it takes the pairs object. Inside the pairs object, there are also references to the original data sets. So inside the pairs object, there's a reference stored to the original data sets. You can also supply the data sets again to compare pairs function, but if you don't, it takes the x and the y attributes of the pairs object. It then takes these variables from the two data sets and compares them on these variables, and then it generates a new pairs object with the new variables added. So what we see here, we have, of course, compared record 1 to record 342 of the second one, and we see that this record only agrees on sex and not on any of the other variables. And for example, this second pair doesn't agree on anything. And here you have, for example, a record that agrees on everything. So this is almost certainly belonging to the same, these two records, basically record 1, record 3,373. These belong almost certainly to the same person. Well, this one, for example, is very unlikely that these two records belong to the same person, because they only agree on sex and not on anything else. Yeah. Well, the next step is to basically translate these comparison vectors into a score. I will start by using a simple scoring method, and later on we will be using more complex methods. Because this is basically, yeah, I mean scoring these comparison vectors is basically in a sense the most important part of record linkage, and also the most complex part. You have to basically to classify your pairs into basically matches and non-matches based on these comparison vectors. So a really simple method of scoring, what we call similarity sum. So basically it's a sum of the similarity function of the similarity scores. You give it the pairs, and optionally also say what variable it has to create, but if you don't, it basically creates a variable called simsum. But basically sum is the sum of these comparison vectors. So over here we see, for example, this record, there was complete agreement, so it's a similarity sum of 6. This one didn't agree on anything, and it's a similarity sum of 0. So we can also see P is it basically a data frame, so that you can do anything you want that you can also do with the data frame. So we can easily take a column and create a table of it. So what we see is that this is basically the distribution of these similarities somewhere. So we have 2,000 records that completely agree. We have a couple of records that agree that are only disagreeing on one variable, and then we have a lot of records that hardly agree. And it's quite typical in record linkage. So generally you have basically a two-mode distribution where you have on the one side a lot of records that have a really low score, and then there are a small number of records that have a really high score. For these you can be quite certain that they belong to the same record, and then there is some area in the middle that is a bit uncertain. And the next step basically now is to determine how certain, at what point you want to classify pairs into matches and non-matches. So, for example, those records with a similarity sum of 4, are these actually belong to the same person, or are these records that are very likely to belong to different persons? And what we can do, maybe we can have a look at some of those records. Let's look at the pairs with a similarity sum 4. I'll put this code over here. Later. Make this a little bit bigger. So, for example, we have here a record 22 and record 2131 that has a similarity sum of 4, and the record basically agrees on last name, sex, date of birth, month, and postcode, but not on first name. So we can have a look at those two records and see. We can look at what the records are. For example, we take one and the other one. If we look at those two records, what we see is that, well, okay, they agree in year, month. There's an error in month, but it's close. It's only a difference of 1. Date, day, sex is the same, last name is the same, and the first name, well, they don't agree. In this case, it's Matt, and it's Matthew. But looking basically at this, it's quite likely that these two records belong to the same person. So there's a small error in month, and also the first name. They are similar, but not exactly the same. And later on, I will also discuss how you can use string similarity functions to score how similar these names are. But in this case, we use a simple function, so they either agree or they don't agree. In this case, they don't agree. But when looking at it, we can see that, yeah, it is quite likely to be the same first name. So looking at this record, we think, well, in this case, for this record, it's quite likely that these two records belong to the same person. Now we can also look at some other records And that's one way of determining this threshold. So basically, to inspecting records pairs for different threshold values, and to basically in that way determine where you want to put the threshold. So looking only at this one, we would say that maybe a threshold of 4 would be okay. And based on that assumption, I will link the two data sets. The next function we have is a couple of select functions where you can basically select pairs based in this case on a threshold. So we're selecting pairs based on a threshold 4. The only maybe annoying thing is that it's larger than 4. So if I would fill in here exactly 4, it wouldn't select 4, but only 5 and higher. So we have to fill in a number smaller than 4 here to actually be able to select 4. This might be. Would have. Yeah, so I give here a threshold. It selects all records with a. Oh, sorry. No, don't do it. With a similarity score higher than 3.9, and I will derive a new variable that's called selected. If you now look at the pairs. Well, here we had the record that was complete agreement, so we have selected that one, and none of these pairs have been selected. How many records that were selected? So we see that we have selected almost 3,000 records. Usually, it's also good to compare that to the size of the data sets. Data sets are also approximately 3,000 in size, so this doesn't seem like an unreasonable number. So we seem to be linking most of the records from the two data sets to each other. Of course, it depends on your problem if that's something that you expect, but in this case, that's something that we would expect. Yeah. So now we have selected the pairs. In this case, I mean, evaluating the quality of your linkages is quite difficult because in general, yeah, you need to have some kind of true data. Basically, but based on basically only this, we can't really say if the selection is correct or not correct. So what is usually done, as you already mentioned, is that you need to have some kind of data either by manually inspecting pairs or having a sample of records that for which you have other information to be able to say something about the quality of this data set. In this case, we can an ID variable, which is the same across the two data sets. So we can evaluate the quality of our linkage in this case using this ID variable. And you can imagine that in some cases, and this was also the case in our example, a lot of people have an official government ID. These are not always present for all persons, but for part of the records, you might have this ID, and you can use that to say something about the quality. Of course, assuming that the people with a known ID have similar properties as the people without a known ID. But yeah, sometimes often happens that you have some kind of additional data for which you know the truth, basically, and that data you can use to evaluate your leakage. So what I will do is, well, I will add this ID to the pairs. So we have a function add from X, give it to pairs, and then you say which variable you want to add. So we take the variable ID from X and add it to the pairs, and we will call it ID underscore X. And the same way, you can do it for Y. I think there was a question. There was a question There's a question. Let's see. How about a unit in dataset 1, which matches one or more units in dataset 2 and has the same similarity sum score? Yeah, that might happen. So you could have a record, for example, where one record, let's say you have two records of Emily Adams. In one case, the month is perhaps wrong. You have another Emily Adams with a different, for example, date of birth. In both cases, you have the same similarity score. How do you distinguish between those two records? Yeah, you're right. That's a problem in this case. And so what we've done now is we've selected basically all pairs with a value above the threshold. That does mean that you can link one record, for example, record 1 from the dataset to multiple records in the second dataset, or the other way around. Later on, I will discuss how you can make a selection from that. But even that does assume that selection method that I will discuss later. So maybe. So what you can have, for example, if in the selected page you can have, for example, record 1 linked to record 10, also record 1 select to record 20 in the second data set. With a score. So you have basically two pairs. Both of them are selected. In this case, record 1 is linked to multiple data sets in the second data set. Later on, I will discuss different select functions that will only select one of them. But these are still based on the score. So it will try to select the one with the highest score if possible. So if you have exactly the same score, yeah, those functions will basically randomly select one of the two. So if you have exactly the same score, then you have an issue. Then it's difficult to distinguish which one you should select. And the select functions that are present in the package will select one of the two, basically at random. Yeah, in practice, I mean, in this example, I used the fact that I mean, in this case, there are only 6 different values you can have for the similarity summary. In practice, as soon as you start working with string distances and you are working with more traditional record linkage methods by your SML model, then differences in, for example, sex will give a different weight of differences in, for example, month. So the probability of having 2 records with exactly the same score becomes really, really small. So in practice, when you start using more complex methods, then the probability of having exactly the same score is almost 0. Yeah, so I hope that answers the question. And if not, see you. Thank you. Yeah, thank you. But I will the select functions. So we have methods, greedy and N2M, that forces basically one-to-one linkage. There are two methods to do force one-to-one linkage. Yeah, so I will continue where I was. I've added the 2 IDs, and I can also check if they are equal. So in this case, this was the one with the high score. So we can, in this case, the 2 IDs agree. So this one is a correct link, and this one, shouldn't be a correct link. And I think that we haven't selected it, so that's okay. But now we can add a variable true, where we say, okay. What we now can do is basically create a confusion matrix where we have compare the selection to the truth. In this case, we know the truth for the entire data set, but in practice, of course, you will probably only have this for a sample of the data set. So what we see here, we are actually doing quite okay. So what we've done, these are our pairs. So what's typical in reclin is that you have a lot of pairs that are in the false corner. It's also what you saw earlier. You have a lot of pairs with a really low similarity score. If correctly linked, 2,955 records, and we have something like 30 errors in this case in our record linkage. So this is actually quite okay already with such a simple measure. Let me see where I am in my talk. Yeah. So what I now would like to do is to basically what I'm going to do is I'm going to stop talking for something like 10 minutes. And I'm going to ask you to basically try to open the exercises. So the link to the data is in the YouTube channel. You can download the example data sets, so the ones that I've shown here. And basically what the question is asking is basically to similar linkages like this with those two data sets, so the census and the CIS, this text data from England. So these two data sets, and also basically this one, but I'm now working with our data sets from simulated data sets from ONS to test different record linkage algorithms. And this is simulated census data, and this is simulated text data, and I'm hoping that you would basically download the data and try to see if you can link those two data sets to each other using basically roughly the same method as I've demonstrated here. I will give you 10 minutes. So I will continue at 13, what is it now? 20. I will continue my talk, and I hope you are going to try to link those two data sets to each other. And if you have questions or run into stuff, put them in the chat and I will try to answer them. And so I will now stop talking. I have a question from one of the participants. They ask if I want to compare variables that are named differently in the two data sets, do we need to rename them first, or can reclin handle that? That's a good question, which I indeed skipped over. Reclin assumes that the variables that you want to compare are named the same in both data sets. I am working on a new version of reclin, which is not completely backwards compatible. It's what we call reclin 2. The default comparator has the same issue, but there's also another comparison function which is more general, where you can name both in output variables. And you can also compare multiple variables, resulting in one comparison vector and the other way around. So the future version of reclin will be able to handle that. But at the moment, it assumes that the variables should be named the same in both data sets. So that's if it's not, you have to handle that yourself first before using reclin. I have another question from one of the other participants. They ask if you use the storing on disk strategy, if it uses a lazy evaluation. No, it doesn't. If you for example, derive a new variable, then it will generate basically a file on disk containing that variable. At the moment, that basically derives the variable. So if you do a number of steps after each other, so I've not shown it yet, but you can also because most functions accept the pairs object as the first object, you can basically chain those pairs, for example, in using the dplyr syntax, or probably even the new pipe operator. Then it will evaluate each function at the moment it's called, and not do any lazy stuff. Unfortunately, for performance it would actually be quite good, but it would become really complex to build it in such a way. Oh. So the 10 minutes have passed. I hope that you all have been able to try and play around with reclin, and I think probably 10 minutes to really redo all of this might have been a bit too short, but I hope you've come a bit of the way there to at least be able to play around a little bit with reclin. So what I will do now is I will continue. So I will later on, I will add the solutions to the exercises to the repository, so you can also look at them then and see if maybe you've done things differently than I have. Let's see. So now, I will continue with my presentation. For that, I will first do some theory. So I will stop sharing my RStudio, and I will start sharing. Let's see. There it is. I will start sharing another application. So we'll be talking somewhat. What we've done now is that we basically use a really simple scoring method. So we basically calculated the sum of basically the similarity, so the comparison factors. Sorry. And that also means, for example, that you give each variable exactly the same weight. So you put the same weight on errors, for example, in the first name as on errors in the last name, or errors in text, or errors in date of birth. But in practice, there are a number of reasons why you want to give different variables a different weight, basically, when calculating the final score. First, some variables might contain much more errors. So we saw, for example, that I'm sorry. There's a. I got a bit distracted by a question. Is in the chat. At least quite difficult. There are two chats. I'll try to respond later on to your question to see if somebody runs into an error, but I think it's quite difficult for me to solve that. I will continue in my talk, and then later on we have a short break, or when we have another exercise, I will try to see if I can help you with your question. So there are a number of reasons why you want to give different variables a different weight. One of them is that some variables contain more errors than others. For example, we saw that, for example, first name contains quite a lot of errors. So yeah, that means that if for example two records disagree on the first name, that doesn't mean that much, because because there are a lot of errors in the first name, that disagreement could be caused by basically just some spelling errors. Another reason is that some values are more unique than others. For example, if you look, for example, of month of birth or sex, those variables can take only very few values. And even if you take, for example, two random persons in a country, then there's a 50% chance that they agree on sex and 50% chance that they don't. So even if you have two records from two data sets and they agree on, for example, their gender, that doesn't really mean that much. Of course, means something, but it means less than if they, for example, agree, for example, on the last name, which is can take on much more values, and therefore the probability of agreeing, for example, on last name is much. Agreeing on last name by chance is basically much smaller. And this is basically what the traditional linkage, traditional probabilistic linkage tries to handle. So basically calculate different weights for the different variables, and for that it uses a model, which I will now try to explain. So if you look at the pairs, these are all pairs, and they are basically divided into two sets. On the one hand, you have a very small number, usually, of pairs, basically, which should be linked. These are called the matches, and then there's a really big set of pairs that should not be linked. And in the traditional literature, it's called the unmatched set, the unmatches. And what you try to do basically is to determine if a pair belongs in this set or in the other set. Well, what we have, of course, are the comparison factors. So these are usually denoted by gamma. For example, you can, in our case, we used a binary comparison vector. So you can, for example, have something 0, 1, 1, and there are a number of other variables. So this, in this case, this is one possibility for a comparison vector. You have a non-agreement on the first variable, agreement on the second, agreement on the third, etc. So you can also write this as comma 1, comma 2, until comma 3, like that. And of course, the goal is to translate this gamma, basically, this gamma vector into a score. In order to do that, there's a model assumed. So we assume there's a certain probability of observing a given gamma, given that's in a, that the two records belong to the same, basically same person, are a match. And there is, of course, a probability that to observe a given gamma, given that it is in the basically the unmatched set. And the goal of traditional probabilistic linkage is basically to estimate those two probabilities, and then using those probabilities, you can estimate a kind of likelihood ratio. That's basically the log of those two probabilities. And the higher this likelihood ratio, the higher the probability that a pair is actually a match, belongs to M, and the lower this probability, the higher the probability that it belongs to U. And the goal is to estimate these two values. And this one is, these are called the M probability, and this is called the U probability. And traditional record links, a further simplification is made. It is assumed that, of course, these gamma vectors, they consist of a number of elements. It's assumed that these are independent of each other. So that means that we can write the gamma given M as a product of the different elements of the vector. So it's the probability of observing gamma 1 given M times the probability of observing gamma 2 given M, etc. So yeah, so we basically split up this probability by assuming these are independent or conditionally independent, actually. Yeah, and so another simplification is made, and that is that these gammas can only take on two values: value 0 or value 1, or false or true within R. So what we're going to estimate, what we want to estimate, basically, what the probability that gamma 1 equals 1 given M, and then the probability that gamma 1 equals 0 given M is 1 minus, I'm running out of screen, wait a minute, I can scroll. 1 minus the probability of gamma 1 equals 1 given M. So our goal is basically to estimate these probabilities. And the same, of course, you can, the same thing is done with the U probabilities. So this is given M, but given U, we have the same, yeah, basically the same format. Let's see. Yeah, and these probabilities are called yeah. So this one is called the M probability, and these are called the M probabilities. And basically, for each variable, we have a different M probability. So that's basically this one. That's called the M probability. And this is the one we are trying to estimate for each variable, both the M and the U version. So if you have 5 variables, we're trying to estimate basically 10 different probabilities. Just the M probability for each variable and the U probability for each variable. So if we plug in this product into this likelihood, we can rewrite this basically as the log of gamma 1 given M divided by the probability of gamma 1 given U plus the log of gamma 2 given M 2 given U. So it basically becomes a sum and these are called weight 1, and this is the second weight, and we can basically give each variable a score. It's called weights, and then we sum those weights to get the total score. To get back to this one, so we have basically both an M probability for each variable and a U probability. It's also good to also explain how you can interpret those probabilities. One is one given U. So what this probability basically said, what is the probability that two records agree, for example, on the first variable, given that they actually belong to the same record? So why would COM1 be 0? That's basically because one of the records basically contains an error. For example, if the first record, for example, is the first name, what is the probability that the two records agree on the first name, given that they are belong to the same person? Now, one reason why they wouldn't, for example, agree is that there's an error. So basically, these M probabilities are largely determined by basically the amount of errors in the variable. So a variable with a very large number of errors will have a lower M probability. While a variable that hardly contains any errors will have a really high M probability, because as soon as the two records belong to the same person and the records don't contain errors, then the variable should be the same in both data sets. So basically, the M probabilities basically model the errors that are in the data set, and then there are the U probabilities. And the U probability, as you mentioned, what it says is, so you have two records belonging to the same person. You have two records that belong to a different person because they are in the U set. So you have two records from different persons. What is the probability they agree on a certain variable? And that, of course, depends on how unique a variable is. So, for example, if you look at sex or gender, they would expect that the U probability of that variable would be something close to 0.5, because there's roughly, if you have basically a regular population, there's roughly something like 50% of the persons are male, 50% are female. So if you take two random persons that are basically two random persons, the probability that they agree, so comma 1 equals 1, is something like 0.5. But at the same time, if you have, for example, a variable that's very unique, such as last name, then we would expect its U probability to be much smaller. So basically the U probabilities measure basically how unique a variable is, and therefore how much basically information it contains, and the M probability measure how many errors the variable contains. So the goal is, of course, then within probabilistic linkage to estimate these M and U probabilities. And that is usually done with an EM algorithm. Now I will stop sharing. We'll first check if there are no questions about this. No, I don't see any questions. So I will stop this share and I will go back to our studio again. Mark is asking a question in the chat. By multiplying the probabilities, you assume independence. I wonder how important that assumption is. That's a good question. Indeed, independence is assumed. You can show that it's actually conditional independence, but even then, in practice, that independence usually does not hold. Especially if you look, for example, at variables. For example, in our example data set here, we have, for example, a date of birth day, a date of birth month. It's quite likely that if there's an error in the month, then there will also be an error in day, or the other way around. The same is, for example, what also usually happens within probabilistic record linkage that, for example, if an address, then you split it up, you have a postcode, street name, address number. One of the reasons of having, for example, errors within address is if people have moved, for example. Well, in that case, all three variables will change at the same time. So in practice, these the assumption of independence usually does not really hold. Yeah, there's a good thing and a bad thing. So the independence assumption usually does not hold. But in practice, what usually does is the case is that even though the assumption does not completely hold, and generally it is that records that have a high final score and high weight at the end are more likely to belong to the same record. So although the exact weights are not exact, there are errors in it because of, for example, the independence assumption. You can use it to basically sort the pairs from likely to unlikely and still use those weights. The disadvantage is, of course, that because the weights are not exactly correct, and in principle, and I will not discuss it here, but if you go back to the original paper, you can also, if you have to weight and you have the MMU probabilities, you can also say, okay, let's say I want to have a number of false links, a fraction of false links that's below, for example, 1%. You could use that if the estimated probability would be exact to exactly determine which should be the threshold to get a expected number of errors below a certain percentage. In practice, that does not really work because there's quite a lot of uncertainty in the estimated probabilities. So, yeah, good question. In practice, the independence assumption does not hold, but even then, the weights can still be used at least to rank the pairs, and yeah, and are still useful in that way. Yeah. I think it's what I will do now is I think it's good to first just show how we estimate those probabilities with reclin. So what is usually done, an EM algorithm is used. So we have the pairs object, and what we basically have to do is to estimate the probabilities that, for example, first name is false, given that actually is the same record or not the same record. It is a match or not a match. Of course, we don't know which pairs are a match or not a match. So we were missing the data on the true match status. And that's why an EM algorithm is used. And that's of course another reason why there is some uncertainty in the estimated probabilities. Not only in the independence assumption, but we're basically missing the actual true data on which records are a match and which are not a match. And that will also introduce biases and uncertainty in the estimated parameters. What I first do is there's a function within reclin called tabulate patterns. Give it the pairs. And what it does is basically counts how often each combination of, in this case, true or false, occurs in the data set. And using this table, this table is basically input for the EM algorithm. We can calculate it like this and then store it and pass it to the function that I'm about to call. But if we don't, so there's a function proplink EM pairs, and that's it actually. You can also specify, you can also give the table to proplink EM, and also specify which variables should be used. But if you don't, you can just call it like this and shouldn't, of course, assign to the pairs. What it does, it estimates the model using an EM algorithm. So it basically creates this table seen here and then estimates on this table the MMU probabilities. So if we print it, then get the estimated MMU probabilities. So let's just have a look at it to see if it makes sense. And I really urge you to do that always, because as you mentioned, the algorithm basically has to estimate parameters basically without having the actual truth. the true information about which pairs are matches and which are not matches. So it's not unlikely that it converges to something that's really unlikely. In this case, the results are actually quite okay. So what we see, for example, here, as I mentioned, if you look at sex, this is two values, male, female. So records generally have a 50% probability of agreeing, even though they don't belong to the same record. So you have a U probability of 0.5, which is what you basically would expect. Also with month and day, for example, for month, you would expect something in the order of 112, which is almost actually be close. And for day, you would expect something like 1/30 to have basically agreement by chance. And this is actually really close to what you would expect. And what you see is that the U probabilities for first name and last name are much lower, because the probability that two persons have basically the same first and last name is really small. If we then look at the M probability, as you mentioned, the basically model the probability of errors, of having no errors. And what you see is what we already saw, that, for example, first name contains quite some errors. So we see that the M probability of first name is 0.8, so it's not 1. And you see, for example, the other variables, like sex and date of birth, day of birth, have M probability that are close to 1. So these contain very few errors, and the name variables contain much more errors. So this looks okay. And in general, what you want is that the M probabilities should be higher than the U probabilities. So it happens sometimes that it converges to a completely wrong solution. And one way of noting it is that as soon as the M probability is larger than U probabilities, then you're quite sure that you're in trouble. What that would basically mean, if you have an agreement, for example, on name, and the M probability of name is lower than U probability, then basically say if you have an agreement on name, that would indicate that the records do not belong to the same pair, which would be strange. So we have the estimated M and U probabilities. It also estimated the matching probability. This should be approximately equal to the expected number of pairs that you expected number of matches. So you would expect that basically that roughly 2% of your pairs are matches. But this is another parameter that is estimated by the EM algorithm. There's also a summary function. Let's give a bit more information on the screen. So I will move it a bit over to make sure that it fits next to each other. So what it does is, well, this one we've seen, but it also adds the table with patterns. So here we have records that agree on everything. We have 2003 records that agree on everything, and what we see is that these are ordered by weight. So these records are the most likely to be matches, and the lower we get on the table, the less likely it becomes that those records are actually a match. And at the bottom we have the records that don't agree on anything. It also calculated some other stuff. Well, these are the estimated M and U probabilities. And what it finally calculates are the posterior M and U probabilities. I should have actually written those down on the whiteboard thingy. But so what we estimate basically was gamma given M. But using Bayes' rule, you can also convert it to M given gamma. And these are the posterior probabilities. And so this one actually measures what is the probability that this one actually belongs to. This is basically the probability that the two records belong to the same person. So some people use this one to classify other ones. There are also people who use this one to classify the pairs. I do have to mention that also because of the independence assumptions and because of the uncertainty in the estimation of the algorithms, you shouldn't take those probabilities as being exact because you don't know, I mean, the model is not estimated using kind of true data set. There's quite a lot of uncertainty in these estimated probabilities. But yeah, if the model does what it is supposed to do, then those probabilities here basically, yeah. So for the records with this pattern, so the records with this pattern, they have a 97% chance of being actually matches according to the model. Yeah. So we have the model, and now we can use this model to score our pairs. So we take the pairs, score prop link, give it the pairs, we give it the model. Yeah, I will keep it and say which variable it has to add. We now look at the pairs. We see that it has added the weight basically to the pairs, and now we can use this to classify the pairs into matches and non-matches. You can also add. I will not going to do it because the pairs object becomes really big on the screen, but you can also type. With type, you can also specify that you want also, for example, want the MNU probabilities and the posterior probabilities. For example, with type is all, it generates all. But I'm not going to do that now. Otherwise, I'm going to clutter up the screen. Yeah. Now. Let's see. What do we do now? What I will do? Oh, sorry. The pairs are generally a match, and below which they aren't. As you mentioned earlier, you can also use. Sometimes you have true data from another data source. So in this case, what I will be doing is I assume that the probabilities are correctly estimated. So basically, we have here a posterior probability higher than 0.5. So according to the model, these records are more likely a pair than they aren't. So this corresponds to a threshold of 3.8. So I will use that to do a selection. So I will give my pairs a threshold on 3.8. Now I have multiple weight variables in my data set. I will specify which one he has to use. I think it will use the correct one, but just to be sure. Oh, I've overwritten the old one. And now we can again look at how we are doing. So we still have the true variable in the data set, and we can compare the current selection to it. Actually, I don't think I'm completely sure. So I will run this one again, and I will. PM. We have the old selection using the similarity sum score, and this one uses the. I am making. This is the old one using the similarity summary score, and this one is the one using the EM score. So this one was still using the similarity, and this one is the using. Oh. I'll select EM. What we now see is that using using the EM model, using estimated probabilities, we have a slight reduction of the number of errors that we make. So of those 22, we now are able to correctly link 9 of them. So we have a small reduction of the errors. I will check how we are at time. So what I'm going to do, I think I will continue with my demo because we don't have that much time left. I'm taking more time explaining than I was planning. So what I will do is I will continue with the demo. I also see a question in the YouTube chat where Marco asked, what if you have more than 2 data sets to link? Yeah, it's a good question. Linking more than one data set is complex. The usual solution is to sequentially link them. So the general solution is to first link 2 data sets, basically resulting in a 3rd data set, and then linking that 3rd data set to the other data set that you wanted to link to the first 2. So the typical solution is do it sequentially, and then you just, of course, you will try to start with the one where you expect the highest link quality. So you link the first 2 data sets where you expect the highest link quality. You derive a new data set. You can use the information from both data sets to also to make the quality better. For example, if address information, you can decide which one is more likely. If there are errors in the data set, and then you link that one to the 3rd data set. That's how it's usually done. In theory, there are methods that you link multiple data sets at once, but these are, to be honest, I've not really seen any big applications of that. One of the reasons is that it becomes, I mean, in theory, what we've seen, so we have a comparison vector, and you can imagine that if you have 3 data sets, you can still make a comparison vector of triplets instead of pairs. So instead of basically a gamma that's based on data from 2 data sets, you can also have a comparison vector that's based on information from 3 data sets. So you have basically, instead of generating pairs, you start generating, for example, triplets. But the problem is that as I mentioned, in principle, the complexity is for 2 data sets is already of the order n, basically n square. So in principle, it's n row data 1 stamped n row data 2. And this is already a big number. Let's say you have a 3rd data set with similar size. Then you're starting to really get into, I mean, I don't know, how big is it? Okay, we're still in the billions range, but I mean, this is just a small data set. So for large data sets, this quickly becomes infeasible. So in general, the problem is solved sequentially. But thank you for your question. So I will continue with my demo. So now, what we've done now, basically, is compared. We've made a simple comparison. Basically, a variable agrees or doesn't agree, and that makes it, and especially for text-based variables, so first name and last name, that can be quite. That can be insufficient. So from example, we saw that there are, for example, small typing errors in first name, and by having a binary separation into it agree or doesn't agree, even if there's 1 letter difference, it doesn't agree. It's not optimal. So we had, for example, the example with Matt and Matthew. That one doesn't agree, and basically we give it basically the same score false as Susan and Matthew, for example. What you generally want to do with when you have string variables is to use some kind of similarity function. I think this is the example over here. Let's go back to the earlier example. we have two records. The last name agrees, but the first name doesn't agree. Although those names are actually quite, but I mean they are quite close to each other. And you want to give this basically a higher weight than, for example, a comparison between, I don't know, Matthew and Lily, for example. And in both cases, these are now false. But yeah, this one is more likely to be a pair than this one. Yeah, well, fortunately, my colleague Mark has written a string distance package that contains a lot of functions to calculate string similarities. And yeah, reclin contains a few wrappers around those functions to be able to use those within the reclin framework, basically. So we have not all functions within the string list functions have wrappers. There are two reasons for that. First, it has to be translated to a similarity function where we want, basically, in principle, want to have the score between 0 and 1, where 0 is complete disagreement and 1 is complete agreement. And another issue with record linkage is that, as you mentioned, we have a lot of pairs that we have to compare. And some of the string similarity functions can be quite computational intensive. So in general, these ones over here, they are faster than some of the other ones, especially Yarrow-Winkler is often used within record linkage. Also, maybe perhaps for historical reasons, but also because it's one of the faster string comparison functions. And it was also developed in the context of record linkage. So one of the things Yarrow-Winkler distance do is put more emphasis on the first, for example, the first letters. And yeah, usually it's the case if you have, especially with names, will generally have more typing errors towards the end, for example. Yeah, so what Yarrow-Winkler does, it basically compares strings to each other. What all of these functions do is that they return a function, which seems a bit strange, but I will come to that later. So what Yarrow-Winkler does, if you call a function, it gives back a function. So we can store this, and we can call, for example, we can look at what the function does. Give it got that a 1, sorry. And let's compare it to the other one. Make a lot of typing errors, sorry. It should be first name. We see here that the agreement between Matt and Matthew is 0.85. If you take, for example, compare Matthew with Lily, it was the other one, you get the yield is 0, because Matthew and Lily do not share any letters. So by using this function in our comparison, we can distinguish between the case like we have here, for example, Matt and Matthew and Matthew and Lily, for example. We can give the first one a higher score than the second one. Let's see. Yeah, but as I said, when you call these functions over here, what they return is a function, and the reason for that is that the traditional probabilistic linkage, so the LAAN algorithm, expects a table with zeros and ones of true or false values. So what we also need to do is to translate this one to be able to calculate to apply the LAAN algorithm. We need to translate these values to zeros and ones, to true and false values. Later on, these values will be used again, but I'll come to that later. So this function does, it compares but if you give it 2 values, it compares. But if you give it 1 value, it will. So if you assign this to a vector. Sorry, I will take this one. Let's make multiple comparisons. Fine. Like this. And now we're comparing this record to both math and Matthew. So we now have a vector of result. I'll put it in the temporary variable to demonstrate the function. If you now again apply the Yarrow-Winkler function, it will convert this to a true false or true false vector, a binary vector, a logical vector. And how it does that is determined by the parameter you give here. So the default value is 0.95. That means that values above 0.95 are translated to true, and below it are translated to false. But for example, if we lower this, for example, to like this, then we say that we have agreement on the first name and non-agreement on the second name. And this is used internally within the package, especially within the probabilistic linkage, to transform these distances to logical values to estimate the EM algorithm. Yeah. Another thing that it does, I have to mention, is that it also handles missing values. So should, for example, I will copy this and repeat it. Let's say we have the 2 names, but we also have a missing value, for example. Let's repeat this name 3 times. We have a missing value in the second one. It's still correct. What we now have is a missing value over here. That will mean that, yeah, in the EM algorithm doesn't handle missing values, but if we apply the function again, it will transform missing values to false as non-agreement, because it is more likely that the variable that does not agree than it does agree if there's a missing value. So yeah, this function can be used both to compare if you give it 2 vectors, and it can be used to generate a logical vector from the comparison, and that is used within the EM algorithm. Yeah. So what we can now do is to let's just go back up. I will take this function, compare pairs. Still comparing on the same variables. Now we want to compare some variables using a Yarrow-Winkler. In option comparators, this expects a list, and we can say basically for each variable we can give a function which to use to compare. So we can say we want to compare first name using Yarrow-Winkler, 0.85 threshold, for example, last name, also Yarrow-Winkler, 0.9, so we can use a different threshold, for example, for other variables. I have to think, oh, sorry, this shouldn't do this, because that's, what do we have? Last name 6. We want to compare this one using the identical function. Date of birth, day, month, and postcode is the last one. There's also a text field, so we might also want to compare it. Oh, let's just use another one. now I have all variables. Yes. I will run it. This will generate an error. So if you do this, it will generate an error because it says that we are comparing on these variables, but the variables already exist in the data set, and it refuses to override. It refuses to override existing variables, but we can say it. We are fine with it using the override. Yeah, I will. If you have a question in the chat, I will answer it in a moment. So now we have again compared on the same variable, but now we're using a string similarity function. So now we have numeric scores for first name, last name, postcode. Let's see. There's a question in the YouTube chat where somebody asked, "Sorry for bothering you." Okay, but what about if variables are numeric? Is there something like a Euclidean distance to compare values? No, there isn't yet. Yeah. So what? For example, indeed, but for example, you could imagine that, for example, for date of birth, day or year, we have blocked on year, but let's say you have a year. Yeah, it's not unlikely that if there are errors, for example, in these variables, especially like birth year, that these errors, yeah, will be somewhere in the range of the original value. So you can indeed imagine that you want to give, yeah, have also a numeric comparison between numeric values and also translate it to a score between 0 and 1. That is possible. The functions do not exist within reclin. It's not too difficult to write one yourself. I'm now thinking, am I going to demonstrate it? I don't think I have enough time to demonstrate it, but I will give an example later on afterwards in the chat. But you can write your own functions, because also if you look at, for example, the Yarrow-Winkler function, it is basically something like a 6-line function. So it's really easy to write your own function. You have to return a function. Yeah, basically have two options. One is if y is missing, so if you only have one argument, and you have another one if there are 2 arguments, and that's basically it. Let's see. Okay, now we have basically compared the pairs using the string similarity function. And I will copy and paste some code we have used earlier. This one. Oh, no. Copy this. So we can do probabilistic record linkage. So what then does, of course, happens, these numerical comparison translated into binary values to estimate the model. So we still have, if you look at the summary, true false values. For example, if you look at this one, we see that yeah, for example, here we have true, false. It's all translated to binary values, and also the m probabilities are basically, we have m probability for this case last name. However, when applying the EM algorithm, when calculating the weights, these scores are used. So these values, these partial values are used. In general, as I said, there are 2 weights. One if there is agreement, one if there's no agreement. In this case, there's partial agreement. So what happens is that the resulting weight for the first name is somewhere between not agreeing and agreeing. So let's say if the variable does not agree, it gets a score of -10 for this variable. If it does agree, it gets a score of +3, for example. If it agrees 0.72, it gets somewhere basically in between based on the height of this score. So these scores, although they are not used in the EM algorithm, they are used when calculating the weights. So when we do it like this, so we do score prop link. You see here the predicted weights. Yeah, we can't really compare it. It's a bit difficult to compare them to the earlier ones, but we see here there will be a lot more variation within these values than in the previous one, because these scores here are used in calculating these weights. And we can again look at this table to see where we want to put a threshold. So let's see, summary. So let's say we want to select pairs with a probability above 0.5. Where are we? It's over here. So a threshold of, I can still use a threshold of 3.8, for example. Let's we have another selection, and we can, I will copy some code from earlier. So type this in, it's not too difficult. Yeah. This one. What we now see is that what we do now is that we see that we no longer we are not missing links anymore. So all links that are present that are linked, but we now have a couple of false links. So these records are linked, but they shouldn't have been. So that probably means that we should have basically increased this threshold to get a better result. What I've used in my example. So probably if we increase this to a higher number, I see that this one starts to decrease and this one starts to increase. So you have to fine tune exactly where you want the threshold to get an optimal linkage result. To be honest, I'm not completely sure if this is better than it seems to be worse than it was, but yeah. Okay. In general, using this string similarity function will generally result in a much better linkage result. Let's see, I don't have that much time anymore. Let's see how we do that. I only have something like 10 minutes left, so I'm checking to see which topics I will treat and which ones I will skip. Well, I'm almost there, so it should be quite okay. Now we are basically at the last topic I want to discuss, and that is using machine learning. And actually, it's not that difficult. I mean, if we look at this data set, yeah, what we want to do, what we've been doing all of the time. I think there is one thing I still have to do actually. I'm a bit, yeah, I'm skipping. I have to do two things. I will first discuss very shortly machine learning, more the basic idea than actually applying it, and then I will discuss the other thing that's still open. That's actually creating from this set of pairs where we have selected some records an actually linked data set. And also what I mentioned earlier, we may want to apply some forcing where we assume that a record from X can only be linked to one record from Y. In this case, it is possible that one record from X is linked to actually multiple records from the second data set. And usually, most data sets, you're quite sure that each record only corresponds to one person. In that case, you want to enforce that you only link single data sets, single records to each other. And it can also improve quality of your linkage quite substantially. But I will first shortly discuss machine learning yeah, and then I will discuss the other topic. because actually machine learning is not that difficult. We've seen this morning. I don't know if everybody was there this morning, but yeah, of course, we've seen a lot of machine learning application in the sense that this is quite easy actually. If you have the data and this structure, you're already close to applying basically any machine learning method. Because the goal is we have this vector of properties. What we want to do is to basically predict if, in a sense, record linkage is a classification problem. We have two classes, namely matches and non-matches, or unmatches. So we want to divide basically, we want to predict if this record belongs to the matches class or the non-matches class. In order to be able to do that, of course, from machine learning methods, we need in general some training data. In this case, for example, we have here the truth value. In this case, we have it for the entire data set. In practice, of course, you don't have it for the entire data set. But as we mentioned a couple of times already, in general, even when doing more traditional probabilistic, you almost always need the truth for at least a small sample of the data. It can be that you have a manual inspection of your records, or it can be that you have some additional information for a subset of the records for which you can use to identify the true match status. So what we can do basically in machine learning is basically estimate a model that predicts using these properties if it's a match or not. So in a sense, I will use GLM, but you can actually use any method you want. This because we have the true match status, and we basically estimate a model. Name. Yeah, these are all the variables. And now we have two classes, so we use the binomial. And of course, we have to supply the data set. Data is now it gives a warning. The warning is because some of the variables, I'm not really sure which one. There's separation, yeah, this one, and maybe in others too, but sees it everywhere. Yeah, we have complete separation on this variable, and this is causing these warnings. But in general, that still means that you can use the predicted probabilities. So now this model, because we have this issue, we also see that we have really large standard errors, but we can still use the predictions from this model. So what we see here, if sex equals true, then we will predict a very high probability of being a match. So you can basically just predict to predict the probabilities, and then you can use that to divide your pairs into matches and non-matches, and you can basically use all the tools and metrics that you have with basically regular, in this case, regression, but you can also, of course, use machine learning methods such as random forest or XGBoost. It's basically replacing GLM with XGBoost, and you're probably almost ready to go. So that's machine learning, and then I will talk about the final step, and also an important step, and that is translating these pairs with a selection to an actual linked data set. Now what we've used until now is the select threshold function. So that what it does is basically, I mean, you can all use it, it's almost something you don't actually need a function for, because you could always, I mean, it's basically selecting, putting this false where this score is below a certain value. Yeah, but there are also a couple of other functions, select n to m and select greedy. They do the same, only they use a different algorithm. What they do is they force default one-to-one linkage. So they make sure that one record from one data set can only be linked to one record for the other data set. So but you could have an example, let's say these are the selected pairs, we link record 1 to record 2 from record 1 from the other data set with a score of, let's say, 4. We link record 1 to the second one with a score of 3. And we link record 3 to record 2 with a score of 2. Now we've linked record 1 twice. So let's say these are the selected pairs. So here we link record 1 twice. We link it once to record 1 and once to record 2. And we also link here record 2 twice. We link record 2 to 1, and we link record 2 to 3. And what we want to actually link each record only once. And what these functions do is they try to basically force the one-to-one linkage. I will start with this one, select greedy. What that does is it starts with the highest scores, the highest weights. Okay, now how it works, it comes across this pair, so we see that it links record 1 to record 1. Then it comes across this pair, and then see, okay, record 1 has already been linked, so this one we don't link. Then we end up here, we see record 3 to record 2. Neither of them have already been linked, so we also link this one. So the result will be true, true, false, true, basically. We link the first one and the third one. The way N2M works is more complicated. It tries to optimize the total weight. In this example, it will give exactly the same result, but in practice, it can also make different choices than the greedy one. So what N2M tries to do is it tries to select pairs in such a way that the sum of the weights of the selected pairs is as high as possible. And then generally, that gives a better result than the greedy algorithm. The disadvantage is that it's more computational intensive, so it uses linear programming to solve this problem. And for really large data sets, this becomes quite a difficult computation. So they both do the same. Greedy is faster, N2M is usually better. And it depends on the size of the problem if you have to use this one or basically this one. In this case, select N2M is fast enough. What we're going to do is we're going to posit the pairs with threshold. I think we used 3.8 before. It should link on the VM. And let's see another selection. I hope this also maybe shows a little bit that it's really easy with reclin to try out different settings and compare those to each other. We have a few minutes left, so I will quickly show the result. You can see here that really different. I mean, the quality of the linkage now is drastically improved. We now have no errors. We basically perfect linkage of the two data sets. And that's because previously we had a lot of false links, but apparently these false links were links with records that have already been linked with a higher probability. So by using forcing the N2M linkage, we can remove those links because these records, they were basically secondary links. And then I've only got a few minutes left, so now we can build just in time the final data set. That we have the function link, posit the pairs, and we have to say which variable it has to use. In this case, we have a lot of variables. Let's use the last one. Let's this one. That. And now basically have the final result. So what it basically does is something similar that merges basically does. Is it links the two data sets to each other, resulting in the final output. So we have linked record 1 from X apparently to record 1 from the second data set. These are the fields from the first data set, and these are the fields from the second data set. Yeah, and link also has options to specify if you want basically as merge those. But there are also records where we have, for example, these records, they didn't occur in the first data set, but they do occur in the second one. But these were not linked. So I'm right on time. Yeah, are there still any questions that I can answer? I don't see any questions in the chat. Well, thank you for your attention, and yeah, I hope yeah that you all can.
Bravo, thank you very much, Jan, for this very useful tutorial, very applicable in the official statistics indeed, also in census and in other researches. Very useful. Thank you so much.
Yeah, thank you for having me here. Thank you.
Now it is time to. We have one more comment from Marian. Really nice to define our custom functions for comparison in order to improve the models. Indeed.
Yeah.
Yeah.
And that was one of the goals of reclin, to make it kind of modular, to make it really easy to customize stuff and to adapt it to your specific situation.
To adapt to the needs. Yeah, very nice. Very useful. Thank you. Now it is time to have a break of half an hour, and we will be back with the panel discussion, virtual roundtable by the experts from Statistics Austria, Eurostat, Statistics Netherlands, and World Bank, and from our foundation, Heather Turner. Thank you so much. See you in half an hour.